Hello all and welcome to Physics with Pranav. If you're new to my channel, I'm Pranav. I used to be a CAIE Science and Math student. I've tutored students from around the world in GCSE and A-level physics, and I'm an IGCSE world topper in science from back in 2013. This video is a part of a series for the CAIE IGCSE curriculum, where for each chapter in the curriculum, I explore the key concepts tested based on data from recent past papers. I dive deeper into these concepts so you have a solid understanding of them. And then I show you how these concepts are applied to past paper questions so you feel really confident to ace your exams. This video will look at questions from paper 4, which is the theory paper, and from chapter 5, the forces and matter chapter of the CAIE curriculum. If you are a GCSE student but are not studying the CAIE curriculum, don't worry because the concepts that are tested read across to Edexcel, AQA, and OCR. The methodology used to approach the questions will also serve you well irrespective of the curriculum you're studying in. Essentially, you will still gain value from watching these videos. This video on chapter 5 is one of 4 videos I've made for this chapter. If you want to check out the other 3 videos where I dive deeper into the key tested concepts and show you how they're applied to paper 2, the multiple choice paper, please check out the links in my description below. So without further delay, let's have a look at paper 4 questions for chapter 5, forces and matter. So the first paper we're going to be looking at is October-November 2023. We'll be looking at variant 4.1. So that's the first question that we have on pressure or Hooke's law. So liquids are difficult to compress where gases can be compressed easily. Part A says, explain in terms of particles why it is difficult to compress liquids. So this is again very common in paper 4 where you're going to have questions from different chapters, you know, or rather you're going to have different chapters tested in the same question essentially. And here we have questions from the kinetic model of matter, and this is not a topic that has been covered yet, but I will be making a video about it soon. So we are skipping the question for now, but we will revisit the question later in the future. But if we move on to B, figure 3.1 shows a rectangular block floating in water. The density of water is 1,000 kilogram per meter cubed. So you've got the rectangular block, you've got atmosphere, you've got water, they've shown its base and they've shown a depth from the surface of the liquid. So the area of the base is 0.014 meters square. So that's the base. It's got an area of 0.014 meters square. The base of the block is the depth of 0.087 meter below the surface of the water. So they've given you the depth, you know the density, you know the depth, and you know the gravitational acceleration near the surface of the Earth. So show that the pressure due to the water at the base of the block is approximately 850 pascals. So pressure in the water would be its density multiplied by the gravitational acceleration or the gravitational field strength on Earth multiplied by the depth, and that would give you an answer of 853.5 pascals, which is approximately 850 pascals. The second question asks you to calculate the force on the base of the block caused by the pressure given in B1. So you know that that's a pressure value. And you have to think about, okay, so what equation relates pressure and force? That's force is equal to pressure multiplied by area. You are given the area of the base of the block to be 0.014 meters squared. So if you multiply the pressure by that area, it will give you a force of around 12 newtons. So that is the force on the base of the block caused by the pressure due to the water. The force F is equal to the weight of the block. Calculate the mass of the block. So this isn't quite from the topic that we are exploring, but it is a concept that we have covered before in the chapter on forces and motion. So we know that the weight is a force. It is the mass multiplied by the gravitational field strength or the gravitational acceleration. And we know that if you want to calculate the mass, we have to divide the weight by the gravitational acceleration. So essentially, if we do that, we get a value of 1.22 kilograms, which is what we've got for the mass there. So I think that is the only question in this paper on the topic of forces and matter. So if we move on to the next paper. So let's now look at October-November 2022, variant 4.1. So the first question on the chapter of forces and matter is 2b, which is a nice question on Hooke's law. A student suspends a spring from a clamp stand and measures the length L0 of the spring. So we know that essentially this length here is what's being measured. That's the That's the unextended length of the spring. That is the length of the spring when there is no load attached to it. So figure 2.1 shows the apparatus. You've got this here. The student then suspends loads of different weights from the spring and measures the length of the spring for each load. So those are the loads, or rather each of these little discs is the load, and you can add a few of them onto the system here, and you can just add that to the spring and it will extend different amounts. He then plots a graph of the length of the spring against the weight. Figure 2.2 is the graph that the student plots. So you've got a graph here. I have added a few lines onto it, which we will use in subsequent calculations. But essentially what you have is the length in the y-axis or the vertical axis. You've got the weight in the x-axis or the horizontal axis. And here you've got the curve that the student has plotted. I think based on the concepts we've looked at, you have to see up until which region or up until which point rather the curve is linear, which means it's a straight line. So in that region, the expansion of the spring is elastic. In that region, Hooke's law is observed. In that region, the limit of proportionality has not been breached. So that is essentially the linear section of the curve. And then after a certain point, so we can feel that there is an inflection point somewhere here, the curve essentially, well, it's no longer linear, it becomes non-linear. That means it essentially becomes a curve. And in that region, we are experiencing inelastic expansion. Hooke's law is no longer observed. So that is the region where, when the deforming force is removed, the spring will return not to its original shape, but will remain permanently deformed. So that is quickly what we can decipher from this graph that is given here. But obviously the questions will ask us to step through it anyway, so let's have a look at that. So part 1 says, using figure 2.2, determine the initial length L0 of the spring. So I think one of the things that I want to draw attention to before we do this is that what we have here is not an extension weight graph. What we have here is a length weight graph. We know that Hooke's law only works or rather relates force and extension. So we need to work with extensions and not lengths. In order to get extension from length, you need to subtract the original unextended length of the spring from any length that is plotted to be able to get the extension. And we have to work with extensions in order for Hooke's law to apply. Okay, so now that's out of the way. The first thing we need to be able to do in order to be able to calculate extensions is know the unextended original length of the spring. We saw that this was denoted by L naught. So L naught occurs when there is no weight or force acting on the spring. That is a value of 0. So we look essentially at where the curve that the student has plotted crosses the y-axis. Obviously, if this was an extension versus weight graph, that point would be 0 because there will be no extension when there's no load applied to the spring unless it's already deformed. But in that case, you wouldn't know what the original length is. But in this scenario, because we're looking at lengths there, we don't start at a value of 0. So what is the value then? So we can see that the graph is split into 10 divisions between 0 and 0.2 meters, which means each of the values is 0.02 meters. So you got 0, 0.02, 0.04, 0.06, 0.08, 0.1, 0.12. So that area there where the curve starts off, or where the curve touches the y-axis, also called the y-intercept, is 0.12 meters. So that is the initial length of the spring. The second question asks, state what is meant by the limit of proportionality, and using figure 2.2, determine the weight of the load that causes the spring just to reach the limit of proportionality. So we have gone through this. So limit of proportionality is the point up to which Hooke's law is observed. It's the point up to which any expansion of the object is elastic. It's the point up to which, when the deforming force is removed, the object returns to its original shape and length, right? And how do you identify this point on one of these graphs? The way to do it, whether it's a It doesn't matter if it's an extension force graph or a length force graph. We will be looking for the region where the curve stops being linear. So if we look at this curve here, it's somewhere around this point where the curve stops being linear and starts becoming, well, non-linear or curvy. So that, according to my eyesight, occurs around this point. So I've dropped a line from there onto the x-axis to try and find the weight at which it occurs. Again, you know, between 10 and 12 newtons, we have the graph split into 10 divisions, which means each division is 0.2 newtons, which would give us a value of 10.6 newtons there where we've dropped it. So essentially, the weight at which the limit of proportionality occurs is around 10.6 newtons. And I've said that the limit of proportionality is the point until which the extension observed in the spring is proportional to the force applied to it, i.e. Hooke's law applies in that region. I could also have said that the extension is, or rather the deformation of the object is elastic, which means that when the deforming force is removed, the object returns to its original length and retains its original shape. So third question goes, using figure 2.2, determine the spring constant of the spring. So the spring constant, so we know that force is equal to the spring constant multiplied by the extension. So spring constant will be the force divided by the extension. Obviously, when we have length, we know that we need to subtract from any value of the length the initial value of the length, which was L naught, which has a value of 0.12 to be able to get the extensions. And we need to always, whenever I look at a graph, I do ask, you know, what does the gradient of the graph signify? What does the area under the graph signify? So for the force, weight, load against extension or length graphs, the area under the graph doesn't mean anything because that's going to be force multiplied by the length of the extension, and you know, no such quantity exists. What we have is force is equal to the spring constant multiplied by the extension, not the force multiplied by the extension equals the spring constant. So the area under any of these graphs is irrelevant. It doesn't really equate to any quantity. But the gradient is of interest because the gradient is the change in the y value divided by the change in the x value, or is the rise over the run. And essentially here the change in the y values would be a change in length, the change in the x values would be a change in weight. So what you would have is the length divided by the weight, or the length divided by the force, and that would be the inverse of the spring constant, because the spring constant would be, so F is equal to kx, k is equal to F by x. Here we have the gradient to give us x by f, or rather L by f, and we have to, if we remove L naught from each of the values, we'd get x by f, and that is the inverse of the value of the spring constant. So if we go and look at it, so spring constant is equal to force by extension, which is 1 divided by the gradient of the extension weight graph. So what we have here is not an extension weight graph. What we've got is a length weight graph, so we need to remove the values of extension. So what I've done here while calculating the gradient is I've cheekily picked the spot where there is no extension. So that is essentially the point where we have the original length of the spring, or L naught, so that I'm only dealing with one value for both the extension and the weight, because where L naught occurs, or where the extension is 0, the load is 0 as well, right? And I need 2 points to be able to calculate the gradient. So if one of the points that I pick is 0, 0, in a way, the other point is the only point that I have to deal with. So I picked a point where the load is 10 newtons, and I've got an extension, well, not an extension, but I've got a length of 0.54 meters. So I'd have to subtract 0.12 meters from that to be able to get the extension at that point, which is what I've done here, 0.54 minus 0.12 to get the extension at 2. Extension at 1 is 0. And I've got a weight of 2 minus a weight of 1. So that is essentially 10 minus 0, which is 10. And that gives me a value of 0.042 meters per Newton. Obviously, spring constant will be newtons per meter, or newtons per centimeter, or whatever unit of length. So spring constant will be 1 divided by the gradient, which gives me a value of around 24 newtons per meter, which means you need 24 newtons of weight of force to be able to extend the spring by a meter. So that is the question there. If we move on to the next one, so we've got May-June 2023 variant 4.2. So question 3. Figure 3.1 shows a person moving across an ice-covered pond to reach a ball on the ice. Explain why this way of moving across the ice is safer than walking. Use your understanding of pressure in your answer. So the person exerts force on the ice because of their weight, right? And the weight of the person is not going to change whether they are crawling across the ice as shown in this diagram or whether they are walking across the ice. That's not going to change. But what is going to change is the pressure that they exert on the ice. They are going to exert a greater pressure if they're walking on their feet because essentially then their entire weight is acting just on the soles of their feet. And that is a much smaller area than if they were crawling along the ice where they're using a lot of their torso and most of their legs to be able to move along the ice, which means, you know, it's a greater surface area on which the same force, which is their weight, tends to act. So that way there's less pressure applied to the surface of the ice, which means there's less chance of the ice cracking because the ice is quite brittle. So as ice is brittle, it is easier to move across ice by reducing the pressure applied on it. This can be done by increasing the surface area across which the weight acts. Crawling increases the surface area, reducing the pressure applied to the surface, which then ensures that the surface does not crack and enables easier movement, right? So that is the better way to move on ice. Probably feels a bit uncomfortable, but probably the best way to move. So figure 3.2 shows a side view of the pond with a layer of ice floating freely on the water. So that's the ice, that's the water. They picked some point X that is 0.45 meters below the surface of the water. The surface area of the pond is 5 meters square. The surface area would be obviously the area of the surface. If you think of it as a circular area, that's 5 meters square. The mass of the ice is 690 kilograms, okay. The density of the water is 1,000 kilogram per meter cube. Point X is 0.45 meters below the ice. Calculate the pressure at point X due to the ice and the water. So this we've seen is a bit like, you know, it's a situation where you've got two fluids. Sometimes it's the atmosphere and another fluid. Sometimes it's just two fluids. But in this case, instead of a fluid, you've got a solid and a liquid. And essentially, to calculate a point beneath both of them, you need to add the pressure that is exerted because of this layer of ice plus the pressure exerted because of this depth of water. So the pressure because of the ice is going to be the force divided by the area. So we know that the area would be the surface area of the pond, and the force would be because of the weight of the ice, and the weight of the ice would be because of its mass multiplied by the gravitational field strength. So we've got that. So the weight is 690 multiplied by 10. This is well, actually it should be 9.81 because we are dealing with a 2023 paper, but I have multiplied it by 10. My answer is not going to be too far off, but just something to be wary of. And I've divided it by the surface area, which is 5 meters squared. It's an SI unit, so I don't have to do any conversion. And that gives me a pressure due to ice of 1,380 pascals. The pressure due to the water is going to be the density of the water multiplied again by the gravitational field strength multiplied by the depth. So again, I've taken a gravitational field strength of 10, and because it's 0.45 meters below, I've had 1,000 multiplied by 10 multiplied by 0.45, which gives me a value of around 4,500 pascals. Again, both of these values will be a little bit smaller if you use a value of 9.81, and then if I add those together to get the total pressure at point X, that gives me a value of 5,880 pascals. Again, if you use 9.81, it'll be a slightly lower value than that, but the methodology still remains to find the pressure at a point where you can have two fluids above it. You could have a solid and a fluid, doesn't matter. The pressure is going to be the pressure because of the two items there, in this case, ice and water. So hopefully that makes sense. It's a chunky 4-mark question, but the concept is simple. You have to apply both the concept of pressure in solids as well as the concept of pressure in fluids. So the next paper is major in 2021. We're going to be looking at variant 4.3. So the very first question here, we've got a question on springs. So figure 1.1 shows a load suspended from a spring. The value of the spring constant K of the spring is 0.2 newtons per centimeter. The spring reaches its limit of proportionality when the load is 15 newtons. So, okay, so you've got 0.2 newtons per centimeter, and it reaches limits of proportionality of 15 newtons. Calculate the extension of the spring when the load is 3 newtons. So the force is equal to the spring constant multiplied by the extension. Essentially, we want to calculate the extension, which means it's going to be the force divided by the spring constant. So here we know the force, we know the spring constant, and if we divide the force by the spring constant, we get a value of 15 centimeters. So if you add a weight of 3 newtons to the spring, you will get an extension of 15 centimeters. To explain what is meant by the limit of proportionality of the spring. So limit of proportionality is the point up until which the extension of the spring is proportional to the force applied to it, i.e. Hooke's law is obeyed. Beyond this limit, force is not proportional to extension and spring is permanently deformed, which means when the deforming force is removed, the spring will not return to its original length and form. So part C, on figure 1.2, sketch an extension load graph for a spring. Label the limit of proportionality with the letter L on your graph. This is quite straightforward. You've got a straight line up till the limit of proportionality, so that red dot is the limit of proportionality. And you have essentially a linear relationship, which means that as the load increases, the extension increases in a linear fashion. And after that, you will still have an extension for the load, but you will get a non-linear extension, which means as the load is increasing, the extension initially increases and then it really doesn't, and then in fact it starts dropping off after a point. So it's yeah, I think it's a classic graph that you can draw. Obviously, I haven't drawn my curve in the best possible way here, but yeah, you should be able to do a better job with a pencil in an exam, hopefully. But that's just something to keep in mind. So the two things they're looking for is you want a linear region up till the spring constant, so you got to up till the limit of proportionality. You got to be able to label that, and you want a non-linear region after that. So those are the two bits that they're looking for. So here, the third, or rather part D, is looking at energy transfers at different positions. That's not something that we have encountered yet, but I'll be making a video on it. You got question 2. Which looks like a question on pressure. So figure 2.1 shows a bookshelf with 2 groups of books, group A and B on it. There are 6 books in each group of books. All the books are identical. The mass of each book is 0.52 kilograms. Okay, so that's group A. They've given you the dimensions. So you got essentially 30 centimeters height, 21 centimeters in breadth, and you have to calculate the length, if you will, because they've given you sort of the width of each of the books. So you have to multiply the width times 6 to be able to get the total width, if you will. I've given something similar here because, again, the books are identical, so you will have the same dimensions, but obviously oriented differently in the case of group B. So explain why the pressure exerted on the shelf by the books in group B is less than the pressure exerted on the shelf by the groups in by the books, not the groups, sorry, in group A. So the pressure is force divided by the area. So in the case of both groups of books, you're going to have the same force because they're going to have the same weight because they all have the same mass. So essentially, the only thing that's influencing pressure would then be the surface area in contact with the shelf. In the case of group A, you're going to have not the 2 longest sides, facing the surface of the shelf. So you're going to have not the sides with the largest surface area, on which the group of books is sitting on. Whereas in group B, you're going to have 21 centimeter, 30 centimeters. That is essentially the 2 longest sides of the book, and essentially that gives you the largest surface area, and the largest surface area is the face that is encountering the shelf for these books. So the pressure is the force divided by the area, and here the force is exerted by the weight of the books. Although both set of books are the same weight, the area over which force acts for group B is greater, and therefore the pressure exerted is lower. So just you got a greater surface area on which this force or this weight acts, whereas it's a smaller surface area for that weight there. Part 2, calculate the pressure exerted on the shelf by the books in group A. So the pressure is the force divided by the area. So the force is going to be the weight, which is the mass multiplied by the gravitational acceleration. Again, it's pre-2023, so you could use a value of 10 meter per second square. And then the mass is going to be the mass of each book multiplied by the total number of books. So it's 0.52 multiplied by 6. And that gives you a total force of 31.2 newtons. And then pressure is force divided by area. So area is going to be the area, the surface area in contact with a shelf. And that's going to be essentially 21 centimeters multiplied by 1.3 multiplied 6 times over, because obviously 1.3 is just the width of one book. You've got 6 books, and you have to convert all of these into SI units because you are using SI units for the force. So 1.3 centimeters, 0.013 meters, 21 centimeters, 0.21 meters. So I've got 0.013 multiplied by 6, and then that multiplied by 21, or rather, sorry, 0.21, and that gives you an area in meters square of 0.0164 meters square. The pressure is then the force divided by the area. Got a force of 31.2 newtons. You got an area of 0.0164 meters square, giving you a total value of 1,905 pascals roughly for the group of books in A. So part B says a diver dives to a depth below the surface of C, where the total pressure is 3 into 10 to the power 5 pascals. Total pressure. So usually when they give you that indication, and if they give you the atmospheric pressure immediately after, that means you need to remember that the total pressure includes the atmospheric pressure. The total pressure is 3 into 10 to the power 5 pascals. The atmospheric pressure is 1 into 10 to the power 5 pascals. The density of the seawater is 1,030 kilogram per meter cube. Calculate the depth of the diver below the surface of the sea. So essentially, the pressure due to the water is going to be dependent on the depth of the water. But before you find the pressure due to the water itself, you have to remove the pressure due to the atmosphere from the total pressure. That's what I've done. Pressure depth is equal to atmospheric pressure plus pressure in water. So put those values out, and that gives me a pressure in water of 2 into 10 to the power 5 pascals. And that is equal to the density of the seawater multiplied by the gravitational acceleration or the gravitational field strength multiplied by the depth, which is what we're trying to find. And then if I plug in the values for density and gravitational acceleration, and then I rearrange the formula so that the depth is the subject of the formula, I get a depth of around 19.42 meters. So the diver is 19.4 meters below the surface of the sea. Quite a few tongue twisters in some of these things. So yeah. So that, I think, is everything. Yeah, that is all the questions on concepts from the topic of forces and matter. So if we move on to the last paper we'll be looking at today, which is February-March 2021. If we go down to try and find the questions on pressure, the very first question is on pressure actually. So 1A, figure 1.1 shows a piece of glass of thickness 2 centimeters and area 0.15 meters squared. Again, 2 centimeters needs to be converted to SI units. The density of the glass is 2.6 into 10 to the power 3 kilogram per meter cube. Calculate the weight of the piece of glass. Okay, so if I want to be able to calculate the weight, I need to know the mass. If I need to know the mass, I've been given essentially the density, and I need to be able to calculate the volume. And if I have the density and the volume, I can get the mass. If I have the mass, I'll be able to get the weight. So the density is 2.6 into 10 to the power 3 kilogram per meter cube. The volume is the area multiplied by the thickness. The thickness needs to be converted into SI units, obviously. So that'll be 0.02 meters. And once I've got that, I'll be able to get the mass. The mass is equal to 7.8 kilograms. So quite a heavy slab of glass. Sorry, again, tongue twisters getting my way today for some reason. And then if I wanted to calculate the weight from the mass, it will be the mass multiplied by the gravitational acceleration. So that's 7.8 multiplied by 10, which gives me a value of 78 newtons. So I've got that there. The second part says the piece of glass shown in figure 1.1 is used as the vertical viewing window of an aquarium. The atmospheric pressure outside the aquarium is 1 into 10 to the power 5 pascals. The average pressure on the inside of the aquarium window is 1.3 into 10 to the power 5 pascals. Okay, Calculate the resultant force acting on the window due to these pressures and state the direction in which it acts. So this is a very interesting question. Usually when they give you atmospheric pressure, and total pressure, you know that the atmospheric pressure is acting in the same direction as the liquid pressure. But in this scenario here, we have something slightly different, right? Where you've got the pressure from the aquarium acting on one side, and you've got the pressure from the atmosphere acting on the opposite side. So you've got two different pressures acting in different directions. So to calculate the resultant force, you need to know the net pressure, and you need to multiply that by the area of the glass. So the net pressure would be the average pressure inside the aquarium minus the average pressure because of the atmosphere. Now, obviously, it could be either way around. So you could have the atmospheric pressure minus the pressure inside the aquarium, or the other way around. The reason I've done it the reason I've done it in the order that I've done it is because the average pressure inside the aquarium is greater than the average pressure because of the atmosphere. So I've just subtracted it out, and then I multiplied it by the area, which is 0.15 meters squared that's given to us. So that essentially gives us a resultant force of 4,500 newtons. Yeah, because force is pressure multiplied by area, but in this case, we are looking at the net pressure because we have, two pressures acting in opposite directions, cancelling each other out in some way, which gives you out a resultant force of 4,500 newtons. And it will be acting sort of outwards from the aquarium or towards the atmosphere because, the pressure due to the aquarium is greater than the pressure due to the atmosphere. If the other way around, you would have the pressure acting sort of inwards, into the aquarium, but in this case, it's going to be acting outwards towards the atmosphere. So it's towards the side facing the air, which is what I've written out here. So it's an interesting question because, again, like I said, most of the questions, you will have the atmospheric pressure and the pressure due to the liquid or the other object act in the same direction. So you would usually have to, work in a slightly different way to here, where you have the atmosphere and the pressure due to the liquid in the aquarium act in opposite directions. So just an interesting question there. Part C, figure 1.2 shows a vacuum pump connected to the top of a vertical tube. So that's the pump, that's the tube, with its lower end immersed in a tank of liquid. That's a tank of liquid. The pump reduces the pressure above the column to 0, and the pressure at point X is 9.6 into 10 to the power 4 pascals. That's 9.6 into 10 to the power 4 pascals. There you've got a pressure of 0 because the vacuum pump essentially sucks off all the air above it. So they want you to calculate the density of the liquid, right? So what you've got here is you've got 12 meters of liquid. You've got no pressure at the top. And you've got pressure of 9.6 into 10 to the power 4 pascals at the bottom. So we know the pressure is equal to the density multiplied by the gravitational field strength multiplied by the depth. So in this case, we know the depth is 12 meters. We know the gravitational acceleration or field strength to be 10. And we know that 12 meters of this liquid is causing a pressure of 9.6 into 10 to the power 4 or 96,000 pascals. So now if we rearrange this formula for density, we get a density of 800 kilogram per meter cube. So the liquid that is in this tube has a density of 800 kilogram per meter cube. And 12 meters of that liquid will give you a pressure of 96,000 or 9.6 into 10 to the power 4 pascals at its base, or point X as shown. So that is the question on pressure. Are there any other questions on pressure or Hooke's law? Can't seem to find any. Yeah. So hopefully that made sense. And if you found any value from this video, please like, share, and subscribe. Share this video also with people who you think will benefit from it. I look forward to catching you in my next video. Thank you for watching. Bye-bye.